Hey guys, good morning. Welcome to the Aerospace Structure lecture series. Today we are going to see the thermal stress basics and its fundamentals. So in introduction, thermal stress is the internal force induced in the material when its expansion or contraction is restricted. It arises from the temperature change affecting the size and shape of the material or the structure. When the structural elements can't freely expand or contract, this internal force will develop. These stresses can lead the structural crack, damage, deformation or catastrophic failure. This will be usually happened in bridges, engines, pipelines and aerospace structures. Understanding thermal stress is crucial for safe and efficient engineering design. This presentation explores the fundamental calculations and real-world implication of thermal stresses. The causes of thermal stress is primarily by the change in temperature happened in the material. Material expands when heat or contract when it's cold. When expansion or contraction is restrained, the stress developed inside the material will take place. Non-uniform heating like temperature gradient causes the uneven expansion. Sudden temperature changes due to the thermal shock can be dangerous for brittle material. Different metal expand at different rate causes different interface stresses in the composites. Proper design must anticipate and they accommodate thermal movements. Let us take this thermal expansion importance in the different materials like ceramics and metals. Thermal expansion describes how materials dimension changes with temperature. The formula is delta L is equal to alpha L naught and delta T predicts linear dimension changes. Where alpha is thermal coefficient, L is length of the material, T is the change in temperature. The expansion can occur in length wise or area wise and volume wise depend upon the geometry. Engineer must account the thermal expansion in assembly of the structures or the components. Thermal stress in restrained bodies is free object will expand with temperature without stresses. When restrained and the compression expansion is prevented, leading to internal forces, so that the thermal stress be calculated by using the formula sigma is equal to E alpha into delta T. In real world structure, restraint are often partial, not absolute. So designer must balance material choice, operating temperature and the support constraint. Now coming to the types of thermal stresses, one is uniform heating, non-uniform heating. Third one is cyclic thermal stress, thermal gradient stress, residual thermal stress, transient thermal stress. So the pressure cooker is the one of the best example for uniform heating where the whole structure heated equally but it get restrained. For the cooking pan on the stove is a good example for non-uniform heating. The part of the structure heated differently causing stress concentration. Where the oven trays or baking dishes, example for cyclic thermal stress, repeated heating and cooling include fatigue happens in the materials. Glass cup filled with hot water is the best example for thermal gradient stresses. Suddenly temperature difference within the material happen. The welded gate or metal furnitures are the good example for residual thermal stress, locked and stress from manufacturing or welded. Microwave and heating frozen foods are the one of the transient thermal stress example occurs during rapid changes in environment. The metal property affecting the thermal stress are the thermal coefficient, modulus of velocity, yield strength, thermal conductivity, specific heat capacity, phase change of material. There are a few things. Accurate data on this property ensures the reliable thermal stresses analysis. Now coming to the thermal stress calculation, let us take the steel rod fixed with both ends which is heated by it at 50 degrees Celsius. The formula we can use the thermal stress sigma equal to E alpha delta 3 and placing the values will get the thermal stress in the material, which demonstrate the importance of expansion in the joints of the structure. Simplified the example helps engineer to build insulation for real world problems. Now coming to thermal stress in the composite material, Composite material is different material, multiple materials with different values of thermal expansion coefficient. This different expansion causes the internal shears and normal stresses, which makes the bimetallic strips can classify example for control the thermal stress in applications. In aerospace, bonded composites face several thermal cyclic stresses. The proper adhesive selection can mitigate the delamination risk. Also, the analytical and finite element model predict the behavior of under the thermal loads and thermal stresses, which helps to thermal capability is a key factor in metals selection for composites. The real world applications are bridges, railway tracks, pipelines, aerospace structures, electronic components, nuclear reactors. These are the different application or real-time causes happening in the railway bridges due to temperature change. Railway track, the gap or pre-stress are used to expand and contraction to avoid the failure of the track. Pipeline also the same to avoid the rupture. An aircraft structure handle thermal gradient during flight time condition. These are the few examples to understand the thermal stress in real life application. Now coming to the effect of thermal stresses, one is cracking, buckling, warping, fatigue failure, delamination, and leak and failure avoiding in the pipes, and the catastrophic failure in the long and short buildings due to the seismic vibration or seismic loads. So thermal stress mitigation techniques need to be understood so that we can avoid or to extend the life of the structure. So one is we need to concentrate on expansion joints, free stressing, material selection. This used to lower alpha, that is the thermal expansion coefficient in critical zone. Stress relieving heat treatment so that during the manufacturing process helps to reduce this thermal stress. Coating and insulations avoid the temperature gradient, allowing cleaning gaps between the mechanical assembly, which helps to proper design, minimizing risk and extend the structure lifespan. Let us take this case study of thermal failure in the pipelines. This can be avoided by using the U-shaped expansion loop in the design, which can be regularly monitored for stress crack was introduced or developed. Design guidelines were updated for the thermal conservation. This is the one of the best example for the failure due to the thermal expansion. In this class, we have to take out the few things from the this lecture. Thermal stress can be results in expansion and contraction. We need to concentrate on metal property and the structural design and their effects. Causes can be required simulations and experimental validation so that we can be avoided the mistakes and failure in future cases and the design of structures. This can be application small microelectrics to the large aircraft infrastructures and other components. The thermal stress understanding is essential for the modern engineers. So conclusion, temperature changes are inevitable in real-world engineering systems. So we need to understand the thermal expansion and the contraction so that we can negligible the thermal stress can be in permanent failure in the components. Also, we can concentrate on metal property, directly influencing thermal stress magnitudes. Proper calculation and design also avoids the thermal failure. Field experience and theory must go in hands in hands to avoid the manage thermal stress and ensures the safety and reliability of the structure. Thank you. We'll see you in the next class.